So in this video, I want to go over two topics, and the first is titled Special Priors, which is just some additional vocabulary surrounding priors. I'm going to talk about 4 different types of special priors, and then best practices for selecting a prior. First special prior I want to talk about is this distinction between proper versus improper prior. And to think about that, just think that in the first 6 weeks of this seminar, we're largely dealing with binary dependent variables that will have a binomial likelihood function, and as a consequence, their conjugate pairing is going to be with a beta prior. So this would be a proper beta prior. It would be a beta. An example would be a beta 0.001, 0.001. And this would be an example of beta prior that's improper, a 0, 0. What's the distinction between the two? Well, there's the formula. We're going to use this formula for the beta distribution to arrive at our prior probability of theta. So if we put in 0.001, b is equal to 0.001. If we consider all possible values of theta going from 0 to 1, we integrate that. The area under the curve is going to be equal to 1.0, which is a proper probability distribution. On the other hand, if we put in 0 and 0 and integrate over all possible values of theta, then the area under the curve does not equal 1, and we do not have a proper prior. We have an improper prior. Notwithstanding its impropriety, it is possible to use these improper priors. I'll go over an example. Let's say we had data consisting of y is equal to 6 successes in n is equal to 10 trials. So recall what the formula is going to be for the posterior. It's going to be a beta a star b star, where a star is going to be equal to y plus a, and b star is going to be equal to n minus y plus b. So we've got our n and y values and our a and b values. So with a proper prior, we do the substitutions, and the posterior is going to be a beta 6.001, 4.001, whereas the improper is going to be essentially the same. It's going to be a beta 6.4. So notwithstanding their impropriety, improper priors can be used. Jeffrey priors are really complicated, which is a nice way of saying I really don't understand them. So in some vague conceptual way, the difficulty seems to be we need to have some sort of a prior that's going to work. It's going to be invariant with respect to transformation. So what do I mean by that? I'm going to go over an example, and the example is going to think, okay, sometimes when frequentists are dealing with binary dependent variables, what they'll do is logistic regression. And here's the formula that they would use. So binary dependent variable, interested in theta, the proportion of successors, the probability of success. So that's the probability of success. That's the probability of failure. The ratio is known as the odds. If we take the natural log of those odds, we get what is referred to as a logit, and that logit can be modeled as a linear function of some sort of an independent variable x. We can take this equation and we can rearrange it, essentially a transformation type of thing, and isolate theta, the probability of success, and get this expression. Now, this is what I think is going on conceptually. What I think is going on conceptually is that if we were to specify a flat prior for this configuration, it would not necessarily be a flat prior for this configuration, and that would be a bad thing. So apparently this transformation business and wanting a prior that's going to work irrespective of the transformation applied. The inability to have that was a major criticism against Bayesian, almost killed its development until apparently Jeffries came along and figured it all out. Default priors. They're commonly used. They're non-informative, so typically they're going to be flat, allowing the data to speak for themselves. and they're also typically left unjustified by the user. So 3 books that helped me a lot were Kruschke, 2015, Hobbs and Hooten, 2015, and Kery, 2010. And all 3 of these books, commonly used books, had flat priors throughout. The whole idea is that, talk about this a bit later, is that using the default isn't necessarily the best idea. You're going to see them quite frequently, but when you read papers, if you're doing your own work, you might want to think about something other than the default. Regularizing priors. Regularizing priors are weak priors. They're not flat priors. They've got some information, but not very much. And so if I think about, let theta be the proportion of folks in the faculty of ALs that are female versus non-female. This would be a weak prior. I mean, it's not a flat prior, but, if I think about my experience walking up and down the halls, I could come up with my own personal informed prior that I think would contain a lot more information than this thing here. So what's this notion about regularizing? The whole idea about regularizing is that in hierarchical models, oftentimes, we're going to ignore the advice not to just default to the default. People are going to try to run a hierarchical model with a flat prior, and the model is going to crash. But what often happens, if the flat prior causes the model to crash, sometimes using a weak prior, a regularizing prior, the whole idea about regularizing is that it provides just enough information to permit the model to run. In terms of best practices, here are some. Basic idea is don't default to the default. Don't just blindly go to the default. In all likelihood, you will have some prior information. You will have some prior idea about the values of those parameters, and it's potentially going to give you a better posterior if you rely and take some advantage of that prior information. Irrespective of how you choose your prior, you probably want to do some sensitivity analysis. You want to try a bunch of different priors. If you get the same results irrespective of the choice of priors, then you're likely to be good to go. On the other hand, if the posteriors are not robust with respect to the choice of priors, then you've got a bunch of hard thinking ahead of you. Regardless of what you choose as your prior, you want to be able to justify it, and then assessing model fit. Because the time constraints, I'm not able to go into detail on model fit, but it's something that's going to be very important, irrespective of whether it's Bayesian or frequentist analysis. Because all the conclusions really rest upon the assumption that the underlying model is correct. So it doesn't seem to me that if the underlying assumptions about the world, the way the world is, if those assumptions are incorrect, then I don't think the conclusions are going to be correct. So, just in summary, 2 main topics of this video: best practices and some vocabulary surrounding special priors.